Welcome to AI Podcast. Today we're talking about a new EMNLP paper called NESTFUL, and the quick headline is this. It tests whether language models can plan and execute nested sequences of API calls, and even the strongest models still stumble when steps depend on each other.
So nested as in one call feeds into the next, right? Like you have to use what you just got to do the next thing?
Exactly. Think of making coffee while on a video call. You can't pour until you've ground the beans, and you can't grind until you've measured them. Each step depends on the last. NESTFUL checks whether models can do that kind of dependency juggling with tools.
Got it. Who's behind it?
It's led by Kinjal Basu and Ibrahim Abdelaziz at IBM Research, along with collaborators. The team also released everything so people can actually run the tools and verify results.
That last bit matters. So why did they build a new benchmark? We have a bunch of tool use datasets already, don't we?
We do, but most of them focus on single calls or very shallow sequences. They rarely stress the thing that breaks in the real world, which is passing the right intermediate result into the right parameter of the next call, with the right type, in the right order.
The boring plumbing that makes or breaks an agent.
Right. If a model can't carry the value from step 1 into step 3 and remember whether it's an ID, a list, or a string, your agent looks smart for a moment and then falls over.
So what's different with NESTFUL?
It centers that exact challenge. Each task gives the model a small library of tools, a natural language question, and then expects a valid chain of calls. The gold solution is an executable sequence, and the tools are typed, so arguments have to match what the functions expect. If you pass a city name where an airport code is needed, the evaluation will catch it.
Can you give me a concrete example of a nested chain?
Sure. Say the user asks, find a round-trip flight to the cheapest beach destination next month, then suggest a hotel within walking distance of the arrival airport. The model has to call something to list destinations and prices, pick the cheapest, that's a beach, then pass that airport code into a hotel search, then filter by distance. Miss any of those handoffs and the whole plan unravels.
Okay, that's clear. What's inside the benchmark itself?
2 main slices. One is math reasoning, which might sound surprising, but it's perfect for building repeatable tools like compute area, convert units, or solve a proportion. The other slice is coding-style utilities derived from function docstrings, things like manipulating strings or lists. Together you get more than 1,000 math problems and a few hundred coding tasks, each with an executable tool chain.
So they're not just judging pretty text, they're executing the calls.
Exactly. That's a big deal. They also define several ways to score the model. One is full sequence accuracy, which is strict. Did you produce exactly the same chain as the gold solution, same tools, same arguments, same order? Another is a more forgiving win rate. If your different chain still runs and gets the right final answer, you get credit.
Nice, like driving a different route but still arriving on time.
Perfect analogy.
How did they evaluate models? Were there fancy agent loops involved?
They tried a couple of setups. One is direct prompting with short examples, so the model outputs a JSON list of tool calls in a single go. The other is a React-style loop, where the model can reason step by step and choose the next call, within a small budget of steps. They also give each task a trimmed list of relevant tools, so context stays manageable, which is realistic if you have a directory and retrieval layer in front of your agent.
And the results? How rough is it?
Even the strongest proprietary model only nailed about a quarter of exact sequences. Win rate was better, around 3 out of 5 final answers correct, because some alternative plans still worked. Open models ranged widely, and a few did noticeably better when allowed to reason in a loop rather than spit out the whole plan at once.
So planning with a bit of feedback helps some models catch their own mistakes.
That's the pattern. And the pain points were very consistent. Depth hurts. As soon as the chain requires using outputs from multiple earlier steps, accuracy drops. Variable naming and passing the right type into the next tool are common failure modes.
Mm-hmm. It sounds like the models can describe a plan, but binding the variables is where things get slippery.
Exactly. The language part is easy to bluff. The execution part is binary. Either the value is there and typed correctly or it isn't.
Were there limitations we should keep in mind?
A few. First, the benchmark skews toward math, which is great for control and executability, but not the whole world of messy APIs. Second, everything is offline and deterministic. Real APIs time out, rate limit, or return slightly weird data. Third, each task comes with a curated tool subset. That's practical for evaluation, but in production you often face a much larger catalog.
So external validity is good but not perfect. Still, it's a strong foundation.
I think so. Another subtle point is schema familiarity. Many models haven't been trained to produce exactly the variable and argument formats the benchmark expects. Few shot examples help, but there's still a bit of format friction on top of the reasoning challenge.
What does this mean for teams building agents today?
Treat nested tool use as a first-class problem. If your product requires multi-step plans with data dependencies, assume the model will misbind variables and add guardrails. Use typed function definitions. Validate arguments before execution. Insert lightweight checks between steps, like, is this field actually an integer? And if not, repair it. And give the system a chance to reason and retry, not just fire a single giant plan.
So it's not just prompt engineering. It's prompts plus scaffolding plus validation.
That's right. And one more practical tip. Score your agent with both strict sequence accuracy and win rate. The strict score keeps you honest about planning quality. The win rate captures whether your users still get what they asked for, even if the route is different.
What would you love to see next from this line of work?
Live API tasks with auth and rate limits, more domains like calendaring, search, and analytics, and deeper chains that require revisiting earlier choices. Also, richer failure analytics so we can separate type mismatches from planning errors from hallucinated tools. And for training, multiple schema variants so models learn the concepts, not just one set of variable names.
Right. Make them robust to the many ways real tools are described.
Exactly.
Quick nod to the authors again. You mentioned Basu and Abdelaziz at IBM Research. Thanks to them and the broader team for releasing an executable benchmark. That's generous and honestly necessary for progress.
Totally agree.
All right, give me the 60-second takeaway.
NESTFUL focuses on the hard part of tool use, the nesting. It shows that today's models can often get the final answer, but they're brittle when asked to replicate an exact multi-step plan with correct variable binding and types. The benchmark is open, executable, and a strong yardstick for future improvements. If you build agents, assume nested chains will fail in surprising ways, and design your system to catch and fix those failures.
Nicely put. My one-liner would be plan carefully, validate aggressively, and don't confuse eloquent explanations with reliable execution.
That's the show. This has been AI Podcast. I'm Evan.
I'm Maya. Thanks for listening, and we'll see you next time.